Buongiorno, benvenuti a tutti.
Good morning and welcome everybody. Part of the meeting is being devoted at this point in time to John Paul II. So I'd like to start this conference with a quotation of the speech that John Paul II made at the CERN in Geneva, the great laboratory of physics of which Lucio Rossi will talk about. The Pope made a speech when talking to the scientists in Geneva, and the Pope stated, altogether, only the secrets of matter, the secrets of the composition of matter and of its energy are the ones that you try and understand. This is why all people are interested in understanding part of the mystery. I'm referring to a part of the mystery because faced with the complexity and the immensity of the complexity of things yet to be discovered, you as scientists are extremely humble. There are indeed indivisible components of the matter, and this is indeed the title of the exhibition. What are the forces that act amongst these particles? It is as if these questions would put us back in time while you make progress further, and a more essential question are thus triggered. The exhibition that we've organized and the meeting that we've organized are indeed following suit to these indications, obviously also in combination with the very title of the meeting. So trying to get to the core of these questions, trying to tell a history, actually a number of histories that have been very much the result of these questions being raised, trying to find this backwardness, basically, of the situation when faced with such huge questions, and trying to go beyond with such questions that are essential for knowledge. Along this course, we're going to be led by Professor Lucio Rossi, who's the head of magnets, Cryostats, and Superconductors group at the CERN in Geneva. He's going to talk about his institution. He was associate professor at the Department of Physics of the Milan University. Then in '89, started working at CERN for the development and the construction of the first magnet, i.e. the prototype for the super accelerators, the Large Hadron Collider, LHC, that he's going to talk about. Then in 2001, he left the Milan University, where he again had a chair, and he joined the CERN in Geneva. And indeed, he's coming from Geneva, and I'd like to thank him for coming straight from Geneva here to the meeting. And I believe he's indeed, and we believe he was the most suited person to talk about this exhibition that, by the way, he also contributed to the organization. So having said as much, I'd like to give the floor over to Lucio. First of all, let me thank Professor Gargantini, friend of Mario, the meeting, for inviting me. I'd like to thank them for giving me the opportunity to talk about what we do, because we do difficult things at the CERN. Indeed, it is not that easy to try and look for certainties. As a matter of fact, seeking out certainties is indeed what is most difficult. Everybody's actually is not even asking for certainties, but just for well-being. So perhaps we can start with the slides. Next, please. So what do we do in Geneva? Well, this is the equipment that you have. You can look at these blue devices. You might wonder what is inside. And it is an underground tunnel that lead into the galaxies, as it were, because, as a matter of fact, what we're trying to do is understanding how, what the universe is. And obviously, I'm speaking on my own personal behalf. I'm not speaking on behalf of the organization and the institution. This is a disclaimer that is certainly most necessary. So let's have a look at the core issues here. Why is there an institution such as the CERN, CERN? Well, the question is, as you may read, to answer certain questions. So indeed, we do raise questions. And questions are to be answered with a certain replies. Science is objective. Many people ask whether a certain certainty is scientific, because we feel that a certainty doesn't depend on me and you, doesn't depend on the individual. We have the feeling that certainties don't need your personal commitment. Whereas, we're going to see in a minute, this is not exactly true. Obviously, certainties are also hard to be divided into different fields. Well, particle physics is one of the two extreme in the spectre of knowledge. On the one hand, on the far right, you see what is greater, the infinite, and basically what is the most ultimate question about the origin of the world, because the mankind looking at stars would wonder what is the origin of the universe. Then at the left end, there's also the quest on the smallest unit, and in the midst, basically, we are located as man. If we go to the left, if we go towards what is infinitely small, we basically go towards physics of particles, or particle physics rather. So we develop microscopes, 1/1,000,000th part of a meter. This is the scope. At present, we look at atoms, and they are in the range of nanometers. This is why nanotechnologies are so much developed, because with atoms now we can see them, we can use them, we can handle them. At CERN, we look at a central truth, that is, particles are waves, and we could look at the very fine light with a much finer light. In fact, we can use a much finer light looking at the details of a billionth part of atoms. So we are looking now at the nanotechnologies, and this is basically the scope of our research. So we are trying to look at the smallest, tiniest part of matter. Think about the world as in this scale, with a man being very much at the center of this, and then you see that there's a part of science that looks at what is very, very large. So I have to use telescopes, radio telescopes, space telescopes, and so on and so forth. So this is one end of the spectrum. The other end of the spectrum is what we use the LHC for. I refer to it as an actoscope, because you can look at an billionth of the billionth part of an atom. So many people actually think about the Big Bang. You see that we are very close to the Big Bang. Big Bang is something that we cannot arrive at. You must be humble in what you do. We do difficult things, but nature overtakes us anyway. So there's a quest for science. We discovered that the matter is made up of molecules. Then we discovered that molecules are made up of atoms. Then, as you're going to see in the exhibition, we found that the atom is not indivisible. Indeed, there are constituents as the electrons of the nucleus. Then we discovered that the nucleus is made up of something else. And then some 30, 40 years ago, we realized that there are also different particles making up the nucleus, the core. These are elements that we think are final, like the ultimate particles, the core. So this is something that we can't see, though. So we can be certain and see things that we cannot see with our eyes. With cells, you can use the microscope and see it. So seeing doesn't imply looking just with your eyes, seeing with your eyes. It implies seeing with an putting together, pooling together different sets of knowledge, of sciences. I apologize now for making a personal request to the organizers. I need my case because I can't look at the slides without my spectacles. So I would like to invite again the organizers to bring me my spectacles because I find it very difficult to see. So you see, we have constraints. I'm talking about constraints. We have to cope with our constraints. I'm used to making such presentations with computers, and I always look at the computer. But in this case, I'm too far away from the slides. So bear with me while I wait for my spectacles. So apparently the case is not to be found. I'm still waiting for my case to find my spectacles and read my slides. So going towards what is infinitely small is something that we do to get to know what are the essential elements, but all essential elements are concerned with something that belongs to all the sciences, astrophysics and others. The basic question is to find out where we come from, and if we look at the figures, we find huge numbers like 13.7 billions of years, and even the universe has a huge length. These are finite numbers, though we cannot actually apprehend and understand what this means. So these are huge numbers, but numbers that are finite. This means that we can measure that. And indeed, this is the result of a measurement. We did measure the elementary particles. After 40 years away after developing the idea of chord, we came to a clear outline. Indeed, we refer to that as the standard model, the reference model. Well, this reference model is our new Mendelian table. It tells us about the essential particles. There are 12 of them. There are 6 very large bricks that we refer to as core, and the other one are much lighter, and those are the ones that we term as leptons. And then there is a bar that I try to color out, and those are the force particles. So we understood very complex phenomena. We streamlined them, understanding the basic scaffolding, i.e. the elementary particles. So elementary particles are not just a few of them. There are quite a number. Each particle has an antiparticle, so you see that matter comes in two symmetrical families, matter and antimatter. Many believe that antimatter is just is just a scientific curiosity. This is not true because we use antimatter even in hospital. Just think about the possibility to go to a hospital and undergo a PET analysis. And the positron is the antimatter of the electron. So not only do we know of the existence of antimatter, but that can also be used in our practical life with positron emission tomography, PET, in the hospitals. So when I look at such bricks of this building, then I can think that the Rutherford atoms has vanished, that all my previous certainties have done away with and collapsed. Well, then, does this mean that we don't have the atom as an indivisible unit? Is it so that we don't have the core of the atoms being the nucleus? So Is it so that certainties are totally destroyed? Well, whenever you know something and you learn something else, it seems as if what you knew previously collapsed. But what is true today may seem as if it is not true the day after, but indeed this is not the case, because not only what we understand is not useless, because it is just one step in a long path, a longer direction. It is indeed a stage of non-return. The atom is made up of a nucleus and an electron. This is true. It is not the ultimate truth. It is one step along a direction. Then I have to follow the next step to follow the next dimension of truth. When the idea of the atom was just set forth, at the beginning, it was with some fear that the idea was put forward, because it entailed the two major contradictions. Nucleus in itself cannot be together, cannot stay together. Probably you've studied that, because particles with positive charges cannot stay together. They tend to go away from the other. Electrons, in terms of energy conservation, cannot just turn around the nucleus. It should emit some energy and become unstable. And yet the person who actually set forth the idea of the atomic nucleus did so out of desperation, because all evidences were aiming at stating that that was to be the case, despite there being a problem that was solved along the way on at a different point in time. Thank you for giving me the spectacles. So now we have our Mendelian table. We have the constituent elements, but there is a question mark, as you see on the slide, because this standard model is very much able to explain physics up to a level. So it tells us about these particles, the way the particles interact, but there's something that it misses out. There are a number of questions that remain unanswered. So, as for example, why are there so many particles? Why are there certain types of forces? And what is mass? Why particles have very different mass one from the other? Well, the question is of an essential importance, because mass, together with space and time, are those that determine the quantity of energy in the universe. Without mass, there's no gravitation. There's no possibility to interact. There's no possibility for space and time to exist. So mass is all important. And it may be disturbing to learn that particles have such properties. A Scottish scholar or scientist, Peter Higgs, found mechanisms, and I'm not going to delve on the details, so as to let us understand why particles have different masses, or the masses that they have. So the LHC was devised some 28 years ago to meet this very question, that is, why particles have different masses. What is the origin of that mass? And just think that just after the Larger Hadron Collider had been engineered, our friends in astrophysics have found other most important issues that did not exist previously. We thought that knowing the mass, we would also know the content of the universe. And yet two major questions emerged. One is about dark matter. Through astrophysics, we realized that great part of matter is escaping our understanding. And then we also understood that there is a part of energy that we cannot understand, that could be some kind of anti-gravity, and that is what we term as dark energy. Then once we've answered the problem about the mass, we would basically solve the problem for a very thin part of the problem. When we thought about the Large Hadron Collider, when we thought that learning about the Higgs boson would tell us everything, but we discovered that what we're going to discover only affects some 4% of the universe, only 4% of the masses of the universe. This is quite incredible. So we understand that there's much more than what we see, and yet we cannot name it, tag it, so much so that we talk about dark matter and dark energy. With LHC, we have done something that can tell us, perhaps lead us also to explain about the antimatter. So the accelerator is going to be useful for many different purposes, but the one that it was developed for or built for or engineered for. So what we're here for is to test assumptions. The LHC was developed basing ourselves on a positive assumption. Many believe that science is the result of doubt. This is not the case. Science is the result of positive assumptions to be tested, because the realities are masters. The way is are always willing to change our assumptions and modify them. But we developed an LHC not based on doubts. It costed 5 billion euro, but we did so because we had the reasonable assumptions that we wanted to test. So after a set of discoveries, of unexpected discoveries, then everything basically is leading us to saying that the more reasonable assumption is that that certain thing must exist, despite me not seeing it. This is why I need a test for. This is why I need the Large Hadron Collider for. So the individual is always involved. Science, as is true with all human activities, does require the devotion, the energy of the individuals as well. It is not objective in itself. So not only do we try and understand particles and why do they have masses, we also want to join efforts because we believe that everything comes from one force, the force that we know being very different, as, for example, gravitational force that keeps together the Earth, the Moon, the solar system, and the universe, and then the electromagnetic forces that keep things together, and then the weak nuclear forces that rule processes that are extremely sophisticated, as is the case, for example, for the burning of the sun. That is obviously the essence of life. So all these forces seem to be different, but we firmly believe that they indeed are the representations of one single force that has different aspects at different levels of energy. It might seem strange, and yet we produce certainties. Such certainties open up, pave the way to additional questions, so they don't create doubts, but questions, open questions. The fact that a certainty is something that you can pocket up and leave, obviously, is something wrong. Indeed, a certainty is a dynamic process, because the more you know, the more you want to know. And what are the methods that you use to go along this direction? Seeing and being persuaded is not an evidence. With science, in the scientific community, we're always asked about certainties, but what do we do then? We look at particles, we accelerate such particles, we break them, making them colliding in a more sophisticated way. We could say that these particles are like waves, and we make them as short as possible. So we use a finer and finer light to shed light on the details. So having them collide, I may shed light on smaller and smaller details, getting to see such details that were not visible at an earlier stage. So seeing and be persuaded is not a straightforward evidence, is indeed the result of a positive assumption that has to find a certain procedure, and science has its procedures. But the way science progress is not just one. There are many discoveries that were the result of hard-headed work. At the beginning, things did not look to be truth. I'm an expert on superconductivity, the magnets that are exhibited in the exhibition, and this is the 100th anniversary of superconductivity. 25 years ago, a discovery was made on superconductivity that led to a Nobel Award. Those are the high-temperature superconductor. Well, I had quite a number of conversations with this gentleman. One on the way this was proven had already been studied by other scientists, but those other scientists were not ready to grasp what they had in their hands. Basically, he was the one that had the assumption, and he saw basically that truism that granted him the award as a Nobel laureate. So what I'm saying is that seeing is not enough, or looking is not enough to see. You have to have a ready mind. You have to have the individual looking at something to see it. You cannot just, direct your gaze on something and see. Certainty is something that needs training. These are the methods we use. We want to develop accelerators to have collisions of particles, thus generating very fine light. And this is not enough, because not only do you have to have the light to see, you also need the eyes to see. Indeed, seeing requires light being shed on objects and eyes looking at that light detecting the details. And indeed, we refer to that as detectors. Those are those cylinders around the point of collision. This is the Geneva institution, the CERN, that is very much the progression of Galileo's work. You see the airport in Geneva, you see the LHC tunnel. There are many other tunnels. I don't know whether you can see them from a distance. There are smaller tunnels that make up the chain of the accelerators of the CERN. The LHC is 27 kilometers long. It's 100 meters underground. I'm now going to show you a video to tell you what it's happening. It is not just the LHC, but a number of accelerators that we've been developing over the past 50 years that led to the Large Hadron Collider. So particles are pre-accelerated in smaller accelerators and then in larger accelerators, and then are sent to an orbit in the Large Hadron Collider, and we expect to see the Higgs boson represented by Professor here, Peter Higgs. So CERN is one of the nicest experience showing that you can enhance what you know, and enhancing already held truth is one of the key assets at CERN. So you see that there are major detectors. The one is on the top left anthrax, and in the other one you cannot see the little man that tells you about the size of these devices. This is the machine, the superconductor magnets, and then you have also a cross-section of the same at the exhibition. This is what I developed at CERN. You see the two yellow beams are just drawn in this case. This is something that may be seen, the beams, these yellow beams that penetrate the magnet in counter circulation and crossing at certain points. Well, there are 2,800 packets, and each being a packet of 100 billion atoms. And that is vacuum. To have some collision, we have to make the beam just a 30 micron thin at the collision. So we have to have it very narrow. I am at the CERN because in the 90s in Italy, thanks to the IFN, the first superconductor magnet was developed. And this is something that should make us proud as Italians. Yesterday, we were talking about the certainties on which we can build. Well, certainly, we have to enhance and consider in high esteem the research level of our young students and of our labs in Italy. This is something we should certainly insist on and enhance. I've shown you the device, and this is the detector. So light would be nothing. What would the world be unless man gets to know it? So you need detectors to actually get to see the light. This is the major detector, and you're going to see elements of that in the exhibition. This is the toroid element, and you see what the size of a man after the development of the device. So working at the Large Hadron Collider implies that you have two beams clashing, and we hope to be lucky enough to see whether an X event happens. So we should follow those lines that are there visible. Such detectors are evidenced by cameras that take 40 million pics per second. I don't know how many gigabytes per second are stored by these cameras. So should you have all the data of an LHC being transferred on a hard disk, you would have a heap of 20 kilometers a column. So there's a mass of data that are to be analyzed and cleaned down. So to get to an element of certainty is not easy and effortless. It takes a lot of effort because you're left with heaps and heaps of data that you have to try and analyze. This is the time when the device was to be launched, and Google devoted us the logo when we were there on September the 10th. And then there an accident took place that was a disaster, but that we learned to overcome. There was a part that had been neglected because it was no high technology, so perhaps because we were in a hurry or because we made a mistake, we had neglected certain components. So you have to understand that with such machines, with such devices, the first thing to consider is that they are extremely complex and that you always have to keep the feeling or the sensation of constraint present. Whenever there's a problem, you always have to consider that the problem is showing you the way forward as the progress towards a certainty. Sometimes you make mistakes, but those mistakes are not to disappoint you, but just to point you the way forward. So the constraint is something that is there to be followed, to be taken good care of. And this is what we say to our children. Whenever they make mistake, we always tell them this is not a major problem. You just have to learn by trial and error, and you have to make progress and not make the same mistakes again. So we've learned something. Here you see the beam, and each of those points is a package of 100 million of particles. That was the beginning. We only had some 15 different packages of particles. We can actually take pictures when we throw them away. So these are the first events after the machine had been put back together after the false start. So these are the first event of the Atlas experiment. The first experiment, you see that there is an asymmetry in the red signs, in the red tracks. Indeed, on the top right, there are many of them. On the bottom left, there are very little of them. This is always something indicating something else. So you see that traces increase when we increase the number of the packets. These are two events. Most specifically, an experiment that we saw with the Atlas, pointing out to the fact that the universe had gone through a different stage, like a primordial broth of quartz and gluons. On the top right, you should see the peaks, the yellow and red peaks that are more symmetrical. On the bottom left, there's a peak This is probably due to the fact that plasma of quark and gluons has absorbed something else. So this is something that we are going to test at the beginning of the month of November. This is a snapshot that was made with specific particles that are the heavy ions, not the ones that we use normally, i.e. protons. Based on that, we can only see if we find something very subjective. Just think that to make those images that we just saw, there's a lot of work with thousands of people involved, thousands of people that have been performing analysis, analyzing data. And these are not just but dreams. This is the result. This is of something that we can get to know, so much so that we communicate about that. And we are certainly convinced that truth exists. We are just like small kids. Small kids, when they see something, they call out their friends and say, come and see, come and see. They don't want to see what they see. They don't want to see what they see is made up of. CERN was set up in 89, 22 years ago, to enhance and promote communication. So what is truth does exist and can be shared. This is not my own dream. And actually, this is why the web was set up, to share in real time data, fully persuading that data are always an indicators of something, of a reality. The web is being used also by many people for different purposes. Anyway, the inventors of the web have celebrated the discovery, and that had been devised as a means to share data, fully believing again that communication is key. I told you that we have so many data for LHC at CERN that we have so much data that we developed something else, not the web, but the grid, that is also studied for climate issues and for DNA. I'd like to wrap up after this presentation of what we do at the CERN, identifying what are the roles for questions in the scientific investigation. I believe that you always have to have a limitless and unbiased observation. What is the limit? Is it really limitless? Is it limited without constraint? Well, the constraint is only the good of man. That is the only term of reference. This is not a constraint, but that is, again, the terms of reference, the principle of guidance that we should follow. Indeed, we shouldn't do just all we could do, but only what is good for man. This is the important term of reference. And then you have to open up only if there's something out there. There's a structural aspect whereby I am separated from the others. The exhibition of the meeting last year was analyzing a very nice sentence by the Pope, where he stated that the fact that I could get to know the truth is not to be taken for granted. It is indeed a miracle that should point to something else, that should be indicative of something else. If I look about the investigations that led from the discovery of the atoms to the quark, then, you always have a question being answered by new certainties. These certainties are not ultimate certainty, but they pave the way to new certainties being discovered. So I believe that this is an ongoing process. I believe that the infinite is shown by this very nature of it being unending. And so all what I see, despite it being taken over by new truth, by new certainties, is not useless, but is a step in the process. I'd like to wrap up adding a further comment. It might seem as if there's no connection between what I'm saying and certainty, but I believe that this is all important anyway. This is one of the masters of physics, Enrico Fermi. He set up a school, and usually the major discovery in science are triggered by an exceptional person, like Einstein, for example. Einstein indeed was awarded the Nobel Prize for a minor discovery of his, but nobody actually discovered something as important as Einstein. But what has been more fruitful in history are the schools of sciences, and science is the enhancement of tradition. Tradition keeps the quest alive. And this is an example by Rutherford. I don't know how many Nobel laureates are the result of the Rutherford School. And we should always also keep in mind our Enrico Fermi, the Italian professor. So a master could be either one person or a group, a school of people. And the experience is a process toward a greater certainty. So we covered the distance. We saw that certainty does depend on the individual. The truth is not something that you invent. It's just a law in physics. It's a fact. And when you see something unforeseen, when you are able to grasp it, because many major top scientists failed to discover something that was just before their eyes. But, you know, to see something, you have to have the right eyes and to gaze at the right gaze, as is the case with our everyday life. Science is, again, a human activity, so has the same failures as with any other human activity. So the truth is, it's something that requires also the individual recognizing it. So you have to have the right attitude to make the discovery. I thought about the title of the meeting, Immense Certainty. Immense means that it doesn't stay in our mind, immense. So we can be certain about something that goes beyond the constraints and the borders of our mind. So I believe that this is an unreasonable assumption. There are those who say that science doesn't give any certainty, but just reproducibility. This is something that I don't share. Science, as there are scientists saying that we do things that are repeatable. This is what we do. Well, I believe that my opinion has the same value as the other one. I believe that there's something that doesn't stay in our mind. Giussani taught us that we should consider everything, not just what I'm interested in. And if I do that, I have to say that certainly something I can arrive at with liberty, with freedom. So you have to have energy, devotion, and all the features and characteristics of the human nature. And I believe that affection and freedom are the main components of the individual, and that contribute importantly to the understanding of certainties.
Grazie. Grazie Lucio Rossi.
Thank you very much to Professor Lucio Rossi. Thank you for what you told us. Thank you for what you showed us, which bears testimony to the passion that you put in your scientific work. And this, obviously, is certainly very important in the presentation of the exhibition that I'd like to invite you to go see it. The title of the exhibition plays with the root of the word atom. Atom implies indivisible, whereas, again, the atom has turned out to be divisible, to be made out of different elements. So I'd like to ask a question that has, is matter divisible or indivisible? Rutherford is the scientist who reached an important certainty, stating that the atom is divisible and is not indivisible, as its name would suggest. So the exhibition, in a way, is a way to penetrate the atom with a number of application individuals and tests. The very architecture of the exhibition refers to the model of the first discoveries of Rutherford, with a core at the center and electrons orbitating around the core, the nucleus. The atom is a billionth part of a meter. We would have a much wider premises being covered had we to translate again the same ratio between atoms and the elements of it.
Prevalentemente vuoto.
The atom, anyway, is largely a vacuum structure.
Questo oggetto che era
The exhibition is very much an invitation to penetrate the atom that becomes ever more real and mysterious at the same time. Obviously, we understand that the atom is not just the result of abstract studies, it is part of our own reality. And new questions are triggered on other deeper levels. This is a process that has involved many scientists. We were involved as well in organizing the exhibition. We were based on one important certainty, i.e. that we can get to know reality and nature. The first part of the exhibition refers to some 100 years ago, so before Rutherford existed. We're celebrating an important year for physics. Before Rutherford, many other scientists were trying to invest heavily on reality to try and grasp its secret and its characteristic features. So here you have a number of those scientists, many more are referred to in the exhibition. These people are part of a tradition of knowledge, of wisdom, that is always feeding the basic certainty being that we can get to know about science, we can get to know about the reality surrounding us. There's a second part to the exhibition where you see very much what the lab where such discoveries were made looked like. Greiger, Marsden, Mossadegh contributed to such studies, and that was turned into a school that moved to the Cavendish Laboratory later on, becoming the point of reference for European physics. Soon after. So we represent the lab where the quest for the truth basically had given thrust in scientific investigation, and the exhibition also refers to the individuals, the people that were really the protagonists in this investigation with their trials, tests, and discoveries. You also see the signature of the Nobel laureate explaining how come that electrons could turn around the nucleus without falling within. So this is the part of the exhibition that we developed to enter into a lab of some 100 years ago that was the state of the art for the time. So at that lab, scientists would invest fully to try and find an answer to the urgent questions, and the answers would come over time. This is the same as it is happening at the moment in Geneva. We don't know exactly when all the questions are going to be answered, but over time, through a process, certain assumptions become ever more reliable and are then turned into certainties. So there's no automatic process. You cannot just use all the data, though sophisticated they could be, but data by themselves are not enough to get to the ultimate answer. 100 years ago, for example, they didn't have the computational capacity they have at the moment. But again, now as then, there was no automatic process leading to the discovery. What it needed for a discovery is just a combination of different factors that take us to certain points of no return, certainties on what is happening, on behaviors, on natural phenomena that cannot be doubted because of the very complexity combination of counter-tests and dialogues amongst investigators. So the fact that there's a core in the atom with electrons rotating around it, well, this is certainly a truth. Obviously, there's still much to be understood. Obviously, we haven't understood everything. Rutherford hadn't understood everything there was to understand about the atom. There are still certain elements to be discovered, and yet what has been discovered is a certainty, is a point of no return. And there's no point in questioning such certainties. One more part of the exhibition, additional part of the exhibition, draws from another important discovery that was made some 100 years ago around the Rutherford lab. Discovery does not remain without consequences. There are consequences in terms of further knowledge being developed. And then there are also application consequences. And a number of examples are referred to also in the field of energy. There is a giant photo in the exhibition of the reactor where thermonuclear fission is being studied with applications such as the production of energy and also with investigating purposes, in the diagnostic tools. So these technological elements in the discovery are steps in the process of achieving certainty. So the application forcing you to come to terms with reality, to test yourself with reality, contributes to the development of certainty, is very much one step in the process of certainty. There is an ongoing test and trials process and a shouldering of responsibility to manage in the best possible way the different devices, the different results being obtained. And then, again, as included in the exhibition, you get to see things that are closer to us time-wise. You find the original question on the indivisibility of matter. What do we mean today when we refer to indivisibility of matter? In this process, there are two important elements that i.e. the craving for man to go beyond. There is an ongoing desire that is shared by mankind to go one step further, never to rest on laurels, but to feel like going always one step further. And then nature stands opposite to that. Thanks to the knowledge contributed by scientists and scholars, nature is always providing new things to study and investigate. In the investigation, then, there are certain devices being presented, enabling us to find such discoveries and to detect the new features or the new components of matter at an ever more intimate level. So think about the combination of an ongoing desire and an ongoing availability of things to investigate. This, obviously, is the situation whereby scientists progress and make additional discoveries. You see that there are new particles to be discovered. We do have a standard model, as Professor Rossi just explained us, that we think we may use to explain the subatom reality, perhaps even too much. There is an overwhelming number of particles to be studied, so much so that we have to organize them, set them in order. So both theoreticians and experimenters have tried to set certain things in orders. We were offered a presentation, a schematic presentation of the different truth when we had that Mendelian table, as was said. But obviously things are not so orderly, but the order is the result of hard work in organizing results obtained. The CERN Geneva is indeed the state-of-the-art laboratory where all such discoveries are made. Man can certainly develop certain knowledge. And this is to answer the basic question of the exhibition. So certainly can be developed, even though it might take a very sophisticated mechanisms and weak mechanisms, at least, included. So all individuals, as Professor Rossi has told us, so all individuals contribute to the final discovery. In order to manage such a complex process, you have to have a wider reason, considering all the factors at stake, thus supporting the strong desire for coming to know this reality, while at the same time also supporting the curiosity it takes to go on with certainty and energy along this path. So this is the exhibition as we've tried to organize. I'd like to invite you all to go see the exhibition. I'd like to thank Professor Rossi for coming to the meeting. There's also a little book that you can buy at the exhibition, and I would also like to invite you to look at one of the leaflets that you were given, where a new initiative of the magazine is carrying out. So I'd like to invite you to cover the process that the exhibition has pointed out to you together with Professor Rossi. Thank you very much. And again, I strongly invite you to go visit the exhibition. Thank you.